Hello, my name is James Radke, and I'm presenting my apple crushing system final design for the BSET 8003 Senior Technical Project. The objective of this design was to design a system capable of crushing multiple apples safely and efficiently, and that's to facilitate the production of apple cider. For the initial design, I researched the approximated maximum closing force of the human jaw on the front incisors, and that yielded a value of 55 pounds. Then I went ahead and measured the distance from the joint part of your jaw to the front incisors, and I got a value of 2¼ inch. Using the equation below, calculated the torque of using force times the perpendicular distance, being the distance I measured from the joint to the front teeth, and plugging those in for 55 pounds times 2¼ inch, yielded a torque rating of 123.75 pound-inches. I then went ahead and converted the inches to feet, and that yielded a value of 10.31 pound-foot of torque. Considering since the apples are fairly easy for the human jaw to shear, I designed the system around this torque rating. The belt drive design, using a 0.75 horsepower motor with an input RPM of 3450. The belt drive calculations then yielded a driving sheave, which is the sheave connected to the motor of the system, of 4.5 inch outside diameter, and then the driving sheave, the sheave that operates the crushing unit and facilitates the crushing of the apples, as 19 inch outside diameter. This resulted in a 3.83 speed ratio, and the reduction in RPM and increased size of the sheave provided the torque needed to operate the system. To the left, you can see the free body diagram of the driven sheave, noticing that the diameter is shown, that's the pitch diameter, 18.95 inches. F1 is the tension on the tight side, and F2 is the tension on the slack side. Using these variables, I was able to calculate the torque output at the driven sheave, using the equation T equals R times F1 minus F2, again where R is the radius of the driven sheave, and that's the radius of the pitch diameter. F1 belt tension on the tight side, and F2 the belt tension on the slack side. Went ahead and plugged the values in and got a torque rating of 374.74 pound-inches. I then went and converted the inches to feet again and got a torque output of 31.23 pound-foot of torque. And that's 3 times more than the output of the human jaw. That's given the system a safety factor of 3. Looking at the overall layout of the system, it's mounted on a 42 inch by 36 inch base frame, which is constructed of A36 structural steel angle. Welded to the top is A36 structural steel plate. And you can see in the back is the belt guard, which is covering the belt drive, and that's constructed of sheet metal, which is bended into shape and welded. And there's 2 mounting plates on each side to allow easy installation and removal of the belt guard. Then there's the housing and the chute, and the housing is secured using the brackets that you can see. Those are on each side of the housing. Those are welded to the base frame and the housing. The housing is placed there permanently, and there's a hole on each side allowing the shaft to be passed through, and the crushing unit is mounted on the shaft as well as the driven sheave, and that shaft is secured by the 2 pillow block bearings on each side of the housing. The pillow block bearings are mounted on structural steel angle as well. You can also see the electrical components of the system, which is there's a rocker on-off switch providing easy operation of the electric motor, and an emergency stop button switch in case of an emergency. And there's a square cutout behind the electric motor of the system, providing the pass-through of the wires and connections of the electrical components. The opening below the base frame or the clearance below, is 16.5 inches. This allows for the easy placement and removal of a 5-gallon bucket. 5-gallon bucket is what will be used to collect the pulp, which is the result of crushing the apples. This 5-gallon bucket is, they're approximately 14.5 inches tall, and those will be removed and placed in the next process, which is the squeezing of the pulp, which creates the apple cider. Here's the overall layout with the chute, the housing, and the belt guard removed. As you can see, the shaft is mounted on both pillow block bearings, and the crushing unit, which is a hollow stainless steel cylinder with 2 stainless steel welded plates and bushings mounted within those plates to allow for the torque transfer on the shaft. Along the outside diameter of the crushing unit is grooved stainless steel plates, and you can see the openings cut out within the top plate of the base frame, allowing for the pulp to pass through and for the driven sheave to have clearance to operate within the system. Here's a detail of the components on the shaft. As you can see, the toggle clamps on each side, those allow for the easy removal of the chute, giving you access to the crushing unit as needed for cleaning or replacement. Then you have the pillow block bearings on each side. Those secure the shaft, and those pillow block bearings are again mounted on structural steel angle. You can see the keystock placement along the driven shaft, with the 2 bushings that are placed on the crushing unit and the bushing placed on the driven sheave. There you can see the driven sheave is enclosed in a belt guard, preventing any foreign objects coming in contact with it. And again, that belt guard has two mounting tabs on each side, and they're bolted on to the top plate of the base frame, allowing easy removal and placement. The design outcomes, with an input of 0.75 horsepower and 3450 RPM, it resulted in an output of 810 RPM at the driven shaft. System was designed around the design horsepower, and that's calculated using a service factor, and that service factor was 1.3. That was selected using parameters of a system operating less than 6 hours a day and for heavy shock loading such as crushing. So I take that service factor of 1.3 and multiply it by my input horsepower of 0.75, and I got a system design horsepower of 1. This allowed me to select the 3V belt under the design horsepower and RPM parameters. And the belt drive was selected because it allows for high torque outputs, and it slips under high loads, which are above normal, preventing any damage to the components along the driven shaft. The overall system efficiency is 90%, and the estimated cost of the system is around $1,914. Thank you.